Thank you so much, Wei. Thanks for organizing. Thanks to the whole program committee, to Karen for starting us off in this wonderful program, and to Madeline and for their assistance. I'm so delighted to be here. I was a TA for this program 10 years ago for Lucia Caparasso in her moduli curves course. It's a circle of life. Here I am teaching this course, and I'm about to attend her 60th birthday conference. So it's really meaningful to me to be here. I would love to get to know you all over the course of the week. Please use my first name if you're comfortable with that. Let's see. When I lecture, I really appreciate a sort of like informal, loose atmosphere. I mean, I will lecture, but if you have thoughts, questions, etc., just yell them out. This is for you all. And if there's like a word that I've used that is not familiar, I would like to know that that is the case. I will be happy to either define it or, like refer you to someone or refer you to the problem sessions. But please, let's just communicate about it. I would love that. Okay. So I had called the course Tropical Geometry. This is not going to be by any means an overview of tropical geometry. And it's likely going to be entirely disjoint from what you may have seen in a, for example, textbook called Tropical Geometry by McLagan and Sternfels. None of that will appear here. On the other hand, so what I do want to talk about is a particular story within tropical geometry that I've thought about a lot. And that's the story of tropical curves and their Jacobians. And at the heart of all of this is the story of graphs and metric graphs. So I prepared this lecture and then sat in sort of bemusement and horror as I saw half of it go up on the board earlier. So we are actually, Josephine and I, at least today, are talking in some ways about the same thing, though it may look very different. And I think this is a good thing. In particular, there are going to be, I think, at least two different problems about the matrix tree theorem on the problem set, one from Josephine's set and one from mine. And I think this is all good. So let me start. So this lecture is roughly about graphs, graph theory. They're Jacobians, and if time, but perhaps not, in which case this is detailed on the problem set, they're Laplacians. This you saw, actually, earlier today. Jacobians are in a sense that can be made precise, dual to Laplacians, but I'm just going to start out from the beginning. So first we have to decide what a graph is. That is subtle. Okay, so, I mean, I don't know, maybe you've seen definitions. Maybe you've seen the definition of a simple graph. What's called a simple graph, to be precise. So a simple graph looks like this. So formally, so the definition, it's a finite set, V or V of G, call my graph G, called the vertex set. The elements are called vertices. And then any pair of distinct vertices may or may not be joined by an edge. So to codify that combinatorially, we will choose a finite. The definition of simple graph G is the choice of a following: a finite set V of G and a finite subset. Sorry, this automatically finite. A subset that I'll write E or E of G of the set that will denote henceforth V choose 2. So by this, I mean the set of 2 element subsets of V of G. So for any pair of distinct vertices, either there's an edge or there is not. These are called edges. I'm sorry. The elements of E of G are called edges. The elements of V of G are called vertices. Is this fine? I will not use this definition in a moment. This is to just get started. I mean,
It's good.
Okay. Fine with that person. What about, so what is an isomorphism of graphs? What is an isomorphism of graphs? Okay. You know, like that one and this one. First of all, these are just pictures of graphs. So an isomorphism, you might, well, okay, should I get, let me just leave it to you to ponder. What is an isomorphism? But the kind of graph, the definition, the kind of graph I'll be interested in is what some graph theorists, like classical graph theorists, would call a multigraph. I allow self loops, so to speak, an edge going from a vertex to itself. And I potentially allow multi-edges, so multiple edges between a pair of vertices. So let me give you a drawing of what could, the kind of structure we would like to admit. Something like this. So I want some kind of combinatorialization of a gadget like this. How can we make such a definition? It's not a mathematical question. I'm asking you to sort of codify some intuition. This is the kind of graph that graph theorists would, if being precise, perhaps call a multigraph. So it allows loops and it allows multi-edges, multiple edges. Okay, so this is actually problem 1.1 on my problem set. The problem is for you to invent your own definition of graph. It should, I mean, it is not a precise question, so it can't have a wrong answer by definition. It should try to codify this intuition. And you should, in making that definition, make a precise definition of what an isomorphism of two graphs is. And instead of just doing it out right now, I want to leave that for homework and then come back to it formally next time. But for now, this is our notion of graph, the one on the right. Is it okay? Any questions? Okay. Here's an easy definition. A metric on a graph is formally just a function from the edge set to the positive reals. So it's any function. These numbers associated to the edges are called lengths. So if you wish, you could really build a metric space out of the data of a pair G, comma, L. A metric graph is formally gamma pair G, comma, L, where G is a graph, L is a length function. So like you really can make a metric graph. You take like segments of the appropriate lengths, you glue them at vertices according to the combinatorics prescribed by your graph, you get a metric space. But at the moment, formally, this is what we're studying. And this is a main player, actually. Yes.
So maybe this is stupid.
No.
Like, let's say you have like a multi-graph and you have something that's a loop.
Yeah.
And like, is that considered to have length 0, or does a metric not? Does not well defined?
So the loop can have any length, any positive length you want. So yeah, in principle, you have to think a little bit about what the metric space like. I'm claiming that you can, make sense of, a metric on the resulting space obtained by gluing intervals at vertices. And you have to decide, so you have to decide if I associate numbers to all of these points, all of these edges, then what does it mean to take the distance between that point and that point? You have to decide it'll be some minimum over all possible lengths of geodesic paths, etc. This can be done. It's not actually at all going to, I'm throwing away half of what I'm teaching right now. I'm not going to be using that notion further, actually. But I'm trying to explain why it might be reasonable to call this a metric graph. But if you wish, you can throw out intuition and just say, these are numbers that we shall call lengths. Does that answer your question?
So, yeah.
Ask again if I didn't get it right. Okay. Yeah. Any other comments or questions? Okay. These are a main player. They are very close to, these are remark. These are examples of curves in tropical geometry in a way we will get to define precisely in future lectures. So if you're interested in algebraic geometric aspects, you're probably interested at some point in studying one-dimensional varieties. This is the tropical analog. Oh, what is tropical geometry? First of all, it's a bit of an unfortunate name. It was named supposedly by a group of French mathematicians who were searching for a name for this kind of combinatorialization of algebra and algebraic geometry. And they were aware of the work of the computer scientist / mathematician Imre Simon, who was Hungarian mathematician working and living at that time in Brazil. And he was a pioneer of the algebraic structures behind tropical geometry, and that's the source of the name. Does anyone have questions or comments about that? Okay, so this is just a remark that I wish to keep this as a main player in the lecture series. All right, so my goal today is to associate essentially linear algebraic data to a graph. And I will focus on Jacobians. Laplacians are a dual notion. But I need to set up the linear algebra, and I want to do so carefully. So let me recall some facts about, like, for example, inner product spaces, just starting with the definition of an inner product. So let V be a finite dimensional, is that okay? FD for finite dimensional vector space over R. Then let me remind you from linear algebra that an inner product on V is a symmetric bilinear form. I'll denote it angle brackets. It has two inputs. The inputs are taken from V. The output is a real number. That is positive definite. Sorry, yes, that is positive definite. Meaning that the inner product of V and itself is strictly positive for all non-zero vectors. V. Let me remind you what bilinear is, just so we're sure. So this bilinear, it says like if you pick a fixed vector V and then you, right, so this bilinear form has two input slots. If you stick in a fixed input in the first slot and then regard the result as a function just from V to R, then this is required to be linear. So too is the other one, just for all V. So too is the other one. Sorry, is this notation okay? So I'm sort of giving the notation of like you fix V, you put in the first slot, what remains is a function from V to R, you require it to be linear. Okay. And symmetry means that these are equal. Okay, so this is inner products on a finite dimensional real vector space. So you can see already 2 points of contact of this lecture, as it turns out, with the previous one this morning. One is the centrality of the notion of positive definiteness, and the other is graphs. Any questions? So recall also that, just as you can represent arbitrary linear maps by matrices, you can represent bilinear forms by matrices. So suppose you pick, let me suppose my vector space is G dimensional for some non-negative integer G. If you have a basis for V, then if you take the matrix of all inner products, This is like a G by G matrix, necessarily symmetric by our assumption. This represents the inner product. The inner product in the precise sense that, yeah, how to say it? If you write an arbitrary vector V in terms of your basis, and similarly for W, then you compute the inner product by matrix multiplication. V transpose, oh, sorry, trying very hard to be careful about abstract vectors and, tuples. So this is computed as the product of the 1 by G matrix of V's, the G by G matrix A, and the G by 1 matrix of W's. And this is by linearity. Is it okay? So in this way, we are like singularly focused at the moment on the space, in fact, of positive definite matrices. So let me, let me give some examples. So I mean, maybe the first example is just the identity matrix. Like if E1 through EG were an orthonormal basis, then what's that A? What's that matrix A? It's the identity matrix, exactly. Then A is the identity. And what you recover is the usual inner product, right? So it's the sum of the VI times WI. Is that okay? Standard inner product. And very slightly more generally, let's see, suppose you have an orthogonal basis that's not necessarily orthonormal. So the EIs and EJs are perpendicular, but the EI, the inner product of EI and EI is some LI, positive necessarily. Then what is this matrix? In this case, exactly, it's diagonal with L's. Okay, all good? So now, I'm just gonna rewrite one of the propositions for Josephine Fletcher to recall the notion of positive definiteness. The analogous proposition for positive semi-definite was covered. So recall the following are equivalent for an G by G symmetric real matrix. First, A is positive definite in the sense that V transpose A, V is positive for all vectors V. Non-zero. 2, all the eigenvalues, recalling that this thing is diagonalizable, are strictly positive. 3, the principal minors of A are all positive. This means you pick some subset of the numbers 1 through G, and you take those rows and those same columns, and you evaluate the determinant. That's positive, that's principal minor. And 4, and this one is of most interest to me right now. It's what Josephine said, but again, in the strictly positive definite case. So the 4th is that it's factors. The A factors was X transpose X for some invertible X. GL, GR. Recalling that GL, GR denotes the group of invertible G by G real matrices, the general linear group. And under these equivalent conditions, your matrix is called positive definite. I am most interested in point 4. Can you intuit or eyeball that 1 and 4 are equivalent? 1 is about, like, think about it in terms of inner products. This is like, you have some inner product on R to the G represented by the symmetric matrix A. Every inner product famously has an orthonormal basis from some linear algebra, from some Gram-Schmidt thing. So up to changing basis, every positive definite matrix is the identity matrix. Where by changing basis, I have to do it both on the left by the transpose and the right because of the calculation we did. Is that okay? So that is the verbal, so maybe I just write, this is roughly, you know, every inner product in a finite dimensional vector space, and that's an orthonormal basis. And that's the equivalence. A normal basis. Sorry, I'll deal with that later. Any questions or comments? This is why we can regard, so remember, let me set notation. This already played an important role in the last lecture. This is going to be my notation for this set of positive definite matrices, symmetric matrices. So this is a subset of R G by G symmetric. This is a G plus 1 choose 2 dimensional real vector space, by the way. So this thing lives in a G plus 1 choose 2 dimensional vector space over the reals. And it's not just a set, but it's actually comma. This is the positive definite matrices, and these form an open convex cone in the space of all symmetric matrices. I think this was actually already argued, more or less. Do you believe it? Does this look like an open condition? Perhaps it does. Convexity, I think, was argued. I mean, if you have, yeah, let's see. First of all, oh, what do I even mean? So first of all, I mean open in the sense of the subspace topology of the vector space, the Euclidean space of symmetric matrices. Cone means that if you have a matrix A in your set, then also lambda A is in your set. Or for, you know, a positive real number. And a cone is convex if whenever you have A and B in, then A plus B is also in. Which I think you can read off maybe most easily from condition 1. So it looks like this. Actually, this picture is not just a cartoon, it's a decently good picture of PD2 figure. Let's call this a figure. Because PD2 is an open convex cone inside of 3-dimensional vector space. Yeah, do we agree that there's a 3-dimensional vector space of symmetric 2x2 matrices? So it looks like this, and you know, to draw things, it's often useful to take a cross section. So if I were to draw the cross section, it would look like some open, convex, not polyhedral, round cone. Okay, is everything okay here? So then I just want to tell you that this is a very good example.
Oh, do you have a question?
Oh, yeah, what's up?
How do you think of round? How do you know it's round?
Because I can't, I mean, like, okay, yeah, I can't cut it out by finitely many half spaces, the intersection of finitely many half spaces. How's that?
Good.
Okay, thanks, Daji. Anything else?
And you can fit the curvature
Of the,
of the cone. Like, I mean, it has a metric on it. You must be able to compute something.
I don't, first, I was about to inform everyone that there is a metric on it, and I'm not, I don't know. Okay. From the, okay, sorry, let me give a more authoritative answer. I will tell you the Riemannian metric, sorry, the Riemannian structure. This is like the next thing I want to say, and then you can. All right, that's what I wanted to say. That from 4, so let's investigate the equivalence of 1 and 4. This says that you have a map from the general linear group, which is a Lie group. To positive definite cone, where it exactly takes X to X transpose X. Yeah, there's some redundancy to this map, so it's many to 1. Like, for example, under this map, which matrices are sent to the identity matrix? Sorry, just, yes, exactly. So the fiber over the identity matrix is the orthogonal group. So in other words, right, so let's do it. So if Y is an orthogonal matrix, XY goes to, oh, sorry, did I do this on the right side or the wrong side? It's the wrong side. YX goes to YX transpose XY. Right, X, which is X transpose Y transpose. Oh, Y, thanks. YX. But okay, so the definition of the orthogonal group is it's matrices such that Y transpose Y is the identity. So this is X transpose X. It's exactly saying that if you change basis by an orthonormal, like change whatever. Okay. It's saying that, if you go from a given orthonormal basis to another one, you have not actually changed your inner product. Yeah, what's up?
What is this O of G? I think I just missed that.
Yes, thank you. Thank you for asking. So this is the orthogonal group. So by definition, this is matrices Y such that Y transpose Y equals the identity. So think of it as changes of basis from one to orthonormal to orthogonal group. So in other words, let's just observe. Sorry, nothing crazy is happening here, but we are making a case that this PD is actually has an instantiation as the quotient of this Lie group, GLGR, by which side is this? On the left by OG. In other words, this positive definite cone is what's called a homogeneous space. It's like, I don't know, I guess it's the first homogeneous space you should care about if you, like me, came from combinatorial, exactly. It's a homogeneous space, by which I mean, I claim it has the structure of a Riemannian manifold. With a transitive isometry group. So homogeneous, like, what does this term evoke in your head? Should like roughly mean like everywhere looks like everywhere else. So the definition is that, okay, so let's just call our manifold M temporarily, that the isometries of M viewed in the category of Riemannian manifolds acts transitively on the point of M. Okay, I think none of this is visible from first principles. I want to like say some words, yeah.
What do you mean by quotient and what do you mean by isomorphism?
Okay, all good questions, yeah. So I mean, I'll just say the relevant words, I think that, and then Yeah.
geometric portions?
So yeah, this is a Lie group. This is a maximal compact set, as it turns out, but in particular, a compact subgroup. So one can make sense. Let me see if I have some relevant words in my notes, actually. Yeah. Maybe I'll just write a few words without appropriate justification, of course, but just so we're I don't know, just so we're thinking expansively. This space is like, of course, very important for very concrete things like semi-definite programming, like the kinds of things that are more along the lines of the first lecture. But it's also very important from the perspective of Lie groups and actually from the perspective of cohomology of arithmetic groups. Okay, so let me try to say just maybe some remarks. Like if you have G, a Lie group, K, a compact subgroup. Sorry, let me just do this for my notes. K, a compact subgroup. Then I claim that the quotient, you can make sense of the quotient. Not only, like you can make sense of the quotient as a homogeneous space. Admits the structure. So in particular, it admits a Riemannian metric. Sorry, a Riemannian, what did I say? Riemannian structure. Which I will not give details for. Oh, so if you, like me, are not super familiar with Riemannian manifolds, this is basically like you have a manifold and the tangent spaces all have the structure of like an inner product. That inner product should vary smoothly as you walk around the manifold, Riemannian structure. And this is just asserted at the moment, but I will give you references to the problem sets or something like that. And it's sort of a if and only if, actually. So conversely, if you have M, oh, sorry, and this, let me finish the sentence. Like this thing is visibly a homogeneous space, actually. It's in the same way, like if you have a group and a subgroup, you can consider like the right cosets of that subgroup, but that set still admits a G action. And that action is transitive. In fact, that action is sort of universal among all transitive actions. All transitive actions are isomorphic to the G set G mod H. So same deal. Yes.
I can actually be identity. Can I? Do you want K-maximal or not?
Oh,
Is it?
yeah, okay, you're right.
I don't know, I mean.
Oh yeah, let's say maximal for safety, sorry. I must have dropped the hypothesis, I apologize. Thank you. What was I saying? Yeah, so this is like, by definition, it's a set of cosets. It still admits a G action, which is still homogeneous. So, sorry, the G action still acts transitively in the cosets, like any group always acts on its cosets. So there's a homogeneous space. And conversely, if you have a homogeneous space, then it turns out that it started life in this way. You consider the isometries of M, so isomorphisms of M with itself in the category of Riemannian manifolds. This circle denotes the connected component of the identity, because like the group itself could, which has a geometric structure, could have multiple blobs in it. So take the blob containing the identity. And then this thing certainly acts homogeneously, or as you can check. Sorry, acts transitively, I apologize. On M, and the stabilizer of any point P is compact. Okay, I sort of wanted to give just like the generalities without too much detail. So there's a lot of assertions here, and in particular, the assertion would be that the tangent, so in our situation, I can at least tell you what the structure of the inner product is at the identity matrix, which is a very good example of a positive definite matrix. Equally good as all the other ones by homogeneity, but the tangent space at the identity admits it's identified with the space of symmetric matrices, and it's the inner product given by trace of the product. So A comma B, I think that's the trace. AB, where remember trace means the sum of the diagonals entries. Yeah.
And can you remind me the O of G on the left side, is that we're taking the left cosets?
Oh.
The quotient? Right cosets.
I hope so. Okay, so this is supposed to mean its elements are supposed to mean be like, sorry, elements of the form like, yeah, so that GL, GR acts on the right. Thank you. Okay, other questions? So maybe let's just remember, I should have written what I had said before. This thing being a homogeneous space retains an action of the group. And from this original map, X goes to X transpose X, one deduces that the action, let's see, so if you have a matrix A, yeah, it's acting on the right the way I set it up. Sorry, so it's backwards from some things. So if you have a matrix A and an invertible matrix X, then X acts on the right on A, sending A to X transpose A X, as can be checked by essentially putting together the claims on the previous board. Again, the transitivity of this action is not news to you. It's again the statement that every inner product admits an orthonormal basis. So what is interesting to me is the restriction of the action to not just GLGR, but to a so-called arithmetic subgroup, GLGZ, the integer invertible matrices of size G by G. Sorry, I just realized in my notes, this is underselling PG. I should just write the keyword. In fact, PDG is something stronger called a symmetric space. It's a homogeneous space. A homogeneous space admitting an involution, an involutive isometry, so an involution in a system of the group with an isolated fixed point. I'm not going to use this fact, but it's good to know. This is a very tightly classified case of homogeneous spaces, which in turn are a very tightly, sort of like a very well-structured class of Riemannian manifolds. Here, there's, okay, can you think of an involution on the positive definite cone? Yeah.
Inverting?
Yes. Yeah, exactly. So the inverting furnishes an involutive isometry and it fixes, for example, the identity. Yeah, so this is, again, just to say, when you see these terms in the future, you see in an example. It's an important example. And symmetric spaces admit lots of structure. Okay. Other questions or comments? Yeah, so what the main player actually is not PDG, but the quotient. Oh, sorry, wrong side again. I apologize. the quotient by the arithmetic subgroup. So this is an arithmetic group. It's the z points of a linear algebraic group defined over the rational numbers, for instance. Is this okay? Like we agreed that there's an action of GLGR by conjugation. Let's restrict the action to just the integers. So this is, just to write it all out, this is GLGR mod GLGZ on the right, mod OG on the left. And this is an example, let me finish the sentence here. This is an example of the so-called locally symmetric space. And so now you've seen an example of this. So locally symmetric space, a first definition is, and you'll have to grant me some fudge factor here in the form of finite stabilizers, but it's basically so it admits a universal cover, which is a symmetric space. So it's locally modeled by a symmetric space in particular. And that's visible here where the universal cover is what we started with. So typical examples are like exactly of this form. You take your symmetric space and quotient by the action of an arithmetic subgroup of the transitive group of isometries. Any questions? Yeah.
So, like, I guess the left quotient is in the category of Riemannian manifolds.
Yeah.
And the right quotient is in the category of algebraic.
It still is, yeah, okay, don't bother me about finite stabilizers if that's okay. Then this is still like, it inherits the local structure from that on PDG.
Like, could I think of the first quotient in the category of algebraic?
Like Lie groups, like, so, you know, if you have a Lie group, you quotient by maximal compact. You have the Riemannian structure. Okay. Yeah, sorry, did I answer your question again?
I guess maybe you can move on and if I still have a question.
Okay, let me, I don't know, let me draw a picture.
I have the same question, but.
Okay, I guess I could.
Can you say a question?
Your left quotient is in the category of, like, the two quotients are in different categories.
Oh, okay, so I guess the deal is like, when you take, first of all, I'm not actually an expert. Second of all, if you take the left quotient, you inherit, though this is not, you obtain non-obviously like a Riemannian manifold structure.
Okay.
Now you're in that category. And I claim, you know, like you take some essentially discrete quotient, you still have an induced, locally speaking, you still have an induced Riemannian manifold. So like roughly speaking, again, not worrying about stabilizers. This is a covering space map. So locally one is modeled by the other.
So this thing on the right is a topological space. That's like the.
It's
which
even
is
better.
Extra properties.
Yeah.
But it's not itself a Riemannian manifold. It's just kind of local.
But I mean, it's sort of a local property, so yeah, so same inner product. Okay. I don't know, you can ignore all of this. Let me get to the combinatorics. This is my main object of interest, let's say for today and some of tomorrow. So let me try to quickly draw a picture, but I need to then move on to maybe some combinatorics and graphs to make the problem set make any sense. So we had this picture before. This is a picture of PD2, and then there's some discrete arithmetic group acting on it. And I claim to you without proof that a fundamental domain looks like a cone, over a triangle with one vertex removed at the positive semi-definite boundary. I'm drawing a triangle in the link. So in other words, a cone over this triangle. Staring at the order, and I hope that's clear. This is a real picture. Not cheating. This is not clear, but we'll see some combinatorics dating back to the early 1900s, among others, from Voronoi that makes it possible to compute such pictures, at least in small cases. Okay. So this yellow thing is a decent picture of PD2 mod GL2, see this locally symmetric space. Generally, they look a lot more interesting, very rich. Okay. Let's get some graphs in here. Any further questions before we do that? Okay, yeah, what's up?
Okay, I think I'm struggling with, what do you mean by universal cover here? I think that's,
In the sense of topology, in the sense, yeah.
Okay.
Yeah.
okay, cool.
So you have a covering space, it's contractible.
Okay, yes, okay, thank you.
Yes,
Wait, some like 3D and the zeros.
yeah, it's a cone over this triangle, that's right, so.
Oh, I see, okay.
It's very hard to draw pictures in 3D, so I just took a slice and I drew what you see in the slice. Thank you. Other things? Okay. Let me get some graphs back in here. So suppose you have a metric graph, G and a length L. Let me assume it's connected. So roughly, you can walk from any vertex to any other through a finite sequence of edges. Let me, as topologists do, orient the edges of G arbitrarily for reference. So this is much like choosing a CW structure on your graph. So each edge gets a head and a tail, and you can do it however you want. Is that okay? I claim that all constructions will be independent of choice of orientation. So then we have the following. So this is exactly the boundary map in the sense of like CW complexes or cell complexes from algebraic topology, but I'll just spell it out. We have a free abelian group generated by the edge set, and we have a free abelian group generated by the vertex set. And this orientation allows one to define a boundary map. The boundary map takes an element of this free abelian group as follows. So first of all, I will write elements of this free abelian group as like formal sums of edges. Is that okay? Where the coefficients are integers. And then if I want to tell you what the map does, it suffices to tell you what it does in generators, that is to say single edges. And the answer is that it sends an edge to head minus tail. So if E points to V from W, then it goes to the formal Z-linear combination of vertices V minus W. Okay? This is the boundary map. So then we're in the following situation. Sorry, so far I haven't used the length function at all. This is just like about graphs. But the length function now induces in a very natural way an inner product on the real vector space R to the edges. So just if you tensor up Z to the edges tensored with the reals. Namely, EI inner product with EI is the length of EI, and EI inner product with EJ is 0. So it's exactly it's like one of the examples we brought up at the beginning, where you have an orthogonal, but not necessarily orthonormal basis given by the edges. So, I mean, not much has happened so far. I have a combinatorial map of free abelian groups, which I could certainly interpret also by tensoring with R formally as a map from R to the edges to R to the vertices, and we'll call this stuff sub R and also C. Again, sending E to head minus tail. And the first homology with integer coefficients is defined to be the kernel of the integer boundary map. So it's a subgroup of yeah, maybe you should let's just think about this slowly together. So what is this? We're looking for formal sums of edges that have zero boundary. So if you've done topology, this is maybe familiar. If my edges happen to be oriented like this, sorry, here would be an example where heads and tails cancel out. Is it okay? Or with a different orientation, you just have to choose your signs appropriately. Is it okay? And H1 of GR is the same thing, but you will have real linear combinations of edges with zero boundary map. So now we're actually in a situation where we associate to a metric graph an interesting point of this locally symmetric space. And that is the punchline of this lecture is a definition, essentially. We'll get to that other stuff next time. Because we have the following data associated to a metric graph. We have a real vector space, which is the first homology with real coefficients, which is a vector space over the reals. We have a lattice inside. I hope it's okay. So you have some real vector space here. And then you have some lattice, looks like this, a free abelian group that generates a whole real vector space, but you'll have real coefficients. And this thing, the ambient vector space, it inherits an inner product from the naive one that we put on the whole space of formal linear combinations of edges. So this is restricted from the one defined on R to edges. So we have three pieces of data. We have a real vector space. It has it's like any two of these pieces of data are sort of trivial. If you have a real vector space and an inner product, that's no data because every inner product space is an orthonormal basis. If you have a real vector space and a lattice inside it, that's also no data. They all look the same. But if you have all three, that's interesting data as follows. So I claim that the triple of this data has a well-defined point in in PDG, the positive definite cone mod GZ. I'll tell you what G is in a sec, associated to it. Called the Jacobian. I'll write Jack of gamma, the metric graph. Here, G is the dimension, whatever it is, of H1, the dimension of the cycle space. And for connected graph, this is exactly, I guess, exercise, the number of edges minus the number of vertices plus 1. I don't know if you've seen that calculation before. Dimension of the cycle space of a graph. I mean, from the perspective of homotopy types, all graphs are very boring. You take a connected graph, pick any spanning tree, contract it to a point. That doesn't change the homotopy type. But now what you have is just a bunch of loops on that point, which is a graph that is studied on the problem set. And the number of loops is the number of edges that your graph has in excess of the number of edges in a spanning tree, which was previously calculated to be number of vertices minus 1. Okay, what is this well as a fine point? You know, if you have a lattice, pick any basis for the lattice, H1, GZ. I'm using basis maybe informally. I just mean like a generating set of the free abelian group. Not in the sense of linear, but in the sense of Z modules, in the sense of abelian groups. Then say Z1 for ZG. Then the matrix, then we obtain, once we've chosen a basis, the matrix of inner products of Zi against Cj. And this is positive definite because this was an inner product. This sounds like we chose sorry, wait. So is everything okay so far? I'm saying if you choose a basis like Z1, Z2, then you can, as we argued at the very beginning of this lecture, write down a matrix with respect to that basis that expresses your inner product. It's positive definite matrix. But I chose a basis. If I want to get rid of that choice, I have to quotient by the group of all integer changes of basis, lattice changes of basis. That's exactly GLGZ. The different choice of basis yields the same point in the locally symmetrical space.
Okay, yeah, you have it.
Okay. Any questions? So then let me do, oh, sorry, yeah, just shout out.
Hello. I'm a bit confused about maybe the formula for
Yeah.
the dimension of homology.
Mhm.
Because if you had a graph with like a ton of vertices and like no edges, then I
Not connected. Yes, this is the formula for connected graphs.
Okay, sorry, I must have missed it when you said it.
I buried it somewhere. Somewhere in the board was the word connected. Somewhere. And so for next exercise, you can decide what's the dimension of the first homology for an arbitrary graph. It should involve the number of connected components. Okay. Let me do one example. And then I'm realizing that half the problem set will be postponed till next time, which is just as well. So I'll try to leave instructions about which problems are most relevant. So one example. Consider a theta graph with edges E1 straw theta. E1, E2, E3, with lengths written L sub I, say. What is the Jacobian of this metric graph? So I need to tell it to you by first choosing a basis and then claiming to you that the basis didn't matter. So maybe I'll choose this cycle. So Z1 is E1 minus E2, and Z2 is E2 minus E3. So I could just write down the matrix of inner products, which I claim will be, and you can work this out as an exercise, the following. But what I'd like to do is to write this inner product in terms of taking the basis of Z's, sticking it in via the inclusion of H1 into the real vector space RE, using a matrix, and then composing. So this will look like you may start to see some connections with the previous lecture. Sorry, if it's okay, let me take one more minute to just write this example a bit bigger on the other board. That matrix equals. D1. So you have a 2x3 matrix that expresses putting the cycle space into the ambient vector space of dimension 3. It goes like 1 minus 1 and 1 minus 1. You have a 3x3 matrix that expresses the positive definite inner product that we put on the space spanned by the edges. And then you have the transpose of the first matrix. And this is another way to express that same 2x2 matrix. So this is the Jacobian of the graph. Okay. The connections to Josephine's lecture one, I think, in fact, were not so apparent today, but will be made clearer hopefully next time. And I will also use this association of a Jacobian to a metric graph to start talking about a generalization to the association of a tropical abelian variety to a tropical curve. Thanks for your attention. Sorry to go over that.